besides torsional strain and steric strain, the conformations of cycloalkanes are also affected by angle strain. Now, angle strain is just an increase in energy when bond angles deviate from the optimum tetrahedral angle of 109.5. So when we talk about angle strain, right, this is just an increase in energy when bond angles deviate from the optimum tetrahedral angle of 109.5 degrees. Now, cycloalkanes will distort their shapes to alleviate this angle and torsion strain. And so you can see here that cycloalkanes with more than 3 carbon atoms in the ring aren't flat, and instead they start to get what we call puckered to reduce that strain. And so it's kind of like this kind of jaggedy shape here. And so what we're going to do through this is look at cyclohexane. So when we think about cyclohexane, and I want us to kind of start our journey at the top of the slide here, okay? If we think about cyclohexane, if it were flat, the bond angles, right, would be 120, and that's a lot more than 109.5. And so the angle strain there is pretty intense. And then if it were flat, all the hydrogens would be aligned, and that would be a lot of torsional strain. And so that's not the conformation that it generally stays in. So in reality, cyclohexane adopts a puckered conformation that looks a little like a chair. So it's puckered where these two line up and these two line up, and this goes down and this goes up. So this is like the head of the chair here, and these 4 here are like the body of the chair here, and then this foot part goes down here, and you can see it going down there. Now, we draw this like this, where, and I'm going to go over how to draw it in just a second, but you'll notice this dark line, and the dark line shows it kind of coming out towards you. But the idea is that this is the head, this part here is flat, and this part comes down. The chair conformation is so stable because it eliminates angle strain and torsional strain. So the chair conformation is stable because it eliminates angle, strain, and torsional strain, right? So what we find here, as I've already mentioned, is those angles are 109.5 in this chair conformation, and then all the hydrogens are staggered from each other, and so that's what eliminates that torsional strain. So let's look at the structure of this here with the hydrogens built in here. What we find is when this is in the chair formation and the carbon atoms that are kind of puckered up, they're above the plane, like if it was a flat piece of paper, they'd be sticking up. these are going to point up, and then the ones that are below the plane, they point down, and these alternate. So it's up, down, up, down, up, down. Okay. Each cyclohexane is going to have two different kinds of hydrogens. You are going to have axial hydrogens, and these are located above and below the ring, okay? And the axial ones are shown here labeled in blue, and so you see they alternate up, down, up, down, up, down. It's kind of like if you think about a globe with an axis here, these line up with the axis. Then if you think about a globe and there's the equator, you have these in gray, which are what we call the equatorial hydrogens. And so these are located around the equator, but they're located in the plane of the ring is another way to say it. Okay. Now, when we look here, what you can see is showing this in another way, where if we're in this chair conformation here, the blue carbons are the ones that are up, right? And they're corresponding to those. And then the red carbons are the ones that are down, and they're corresponding to this one, and that one, okay? And so you can see how that corresponds between this visual and this visual. Then, if you look over here, you can also see how the axials are drawn straight up and the equatorials are drawn pointing out, okay? So let's talk about how to draw this representation. So when we want to talk about how to draw the chair form of cyclohexane, the first step is that you need to draw the carbon skeleton. Okay. And the best way that I find to do this is you start by drawing two parallel lines like that. Okay. And then you draw two parallel lines like this. And then you connect them, right? And then you kind of clean it up a little bit, as I am doing right here, right? And so you're drawing the parallel lines, and it's important to know, right, that this atom here, this one here, and this one here, these are in the front. Okay. So those bottom three carbons are coming out of the page. And of course, sometimes the bonds are shown in bold, like I've shown you before. Then step 2, right? You can label the up carbons, right, and down carbons. So when we look at labeling the down carbons, and we're going to do this in blue, the down carbons are here, here, and here, okay? And then the up carbons, we're going to do this in red, are here, here, and here. And so we've labeled those. Then you need to draw the axial hydrogen atoms. Okay? And so when you do this, you do, I like to start with the up carbons, right? And when you do that, the axial hydrogens go up on the up carbons, right? And then right here, and this one is where it gets hard. So you kind of have to draw over the plane there. So you really have to think about this in 3D. These are coming out, and that's drawn up over the plane. Okay? So make sure it's above. Don't mess with it in your bond. Otherwise, that'll really kind of throw off your perception as we talk about drawing it. Then we are going to draw the axial carbons, the axial hydrogens that go down, right? And I'm going to erase these arrows here so that we can see our hydrogens really well. Okay. So in any of the carbons that are down, these come down, and you need to draw this one past that bond and here, because you want to draw this one above this bond and this one past the bond here, so that it's not messing with the bond, the carbon-carbon bonds, or your visual of it. All right, so we've drawn the axial hydrogen atoms, and now we are going to draw the equatorial hydrogen atoms. So and I want to give you a few notes here with the axial hydrogen atoms. These, right, on an up carbon, right, the axial H is up, and then on a down carbon, the axial carbon is down. Okay. Then the fourth step is we're going to draw the equatorial hydrogen atoms, right? And so when we draw the equatorial hydrogen atoms, the axial hydrogen, right? So if we look at a down carbon here, the axial hydrogen is down on a down carbon, so that means the equatorial hydrogen must be up, okay? So on a down carbon, the equatorial hydrogen is up, right? And so we are going to show that kind of drawn out this way. And this one we show drawn this way. And then this one we show drawn this way. And then on an up carbon, the axial hydrogen's already up, so we need to draw the equatorial hydrogen down. Right? So that would go like this. That one would go kind of out like this. That one would go kind of out like this. Now, if you would like to use multiple colors on the exam, you're more than welcome to, but it would behoove you to know how to draw this, okay? So you need to be able to understand how to draw this. Now, just like with ethane, cyclohexane can have different conformers, okay? So when we look at this, cyclohexane can undergo a conformational change called ring flipping, okay? So cyclohexane can undergo a conformational change called ring flipping, okay? When we look at this, right, as a result of a ring flip, so we have the chair form here, the ring flips into boat form here, right? And then a carbon flips down here. What happens is all of the up carbons become down carbons, and all the down carbons become up carbons. So let me write that down, right? As a result of a ring flip, the up carbons become down carbons, right? And the down carbons become up carbons. So look, right? You've got this guy here, and he's in this chair. And then basically, if you can kind of imagine, you push this up to give us this boat form, where now what was the footrest of the chair is now up here, and this looks like a boat, and that's why it's called boat form. Then you take this and you push it down, and now it is chair form. Okay, I highly suggest building this and trying it. Okay, now, and if you want to come by my office, and I'm going to show you this in class, but this is what we see. Okay, so what happens then is that if we go and look at this next image, right, all of the axial and equatorial hydrogens are also interconverted during a ring flip. So that means if your axial hydrogens, which are here in blue, right, they go through the boat conformation, and now they're all equatorial hydrogens also in blue. Okay, so that means the axial and equatorial hydrogen atoms are also interconverted during a ring flip. Right? The axial become equatorial and vice versa. Okay? Now, right? I want to talk a little bit about the boat conformation. So when we come over and look at the boat conformation, that is another conformation. So we've got the chair conformation, and then the boat conformation is the second conformation of cyclohexane. Now, the boat conformation right, are 7 kilocals per mole less stable than the chair forms. Okay, and so that boat conformation is destabilized by the torsional strain, because the hydrogens on the 4 carbons in the plane are eclipsed. Right? And so these then, right, we see these eclipsed hydrogens here, and that's going to cause that torsional strain. Now, you also have steric strain, right? So there's also steric strain, right, because of the flagpole hydrogens. And so when we look at the flagpole hydrogens, those are shown right here and right here, okay? And they are the ones that are forced really close together, and so you end up with a lot of steric strain there. So these are the two reasons, here and here, that the boat conformation are less stable than the chair forms, right? Now, everything we've looked at so far has just had hydrogen atoms, okay? What happens if you maybe have a larger group, right? Like a substituent on there. Well, let's talk about that. So, when you have a substituent, okay, and you need to draw it, the first step is to draw one chair form, right, and add the substituents, right? And so we're gonna draw our chair form. So we're gonna make those two parallel, right? We're gonna make this and that one parallel, and then we'll make that one and that one. Okay, so there's our chair form. Now you arbitrarily pick a ring of the carbon and then classify it as up or down and then draw the bonds, right? So I'm gonna make this guy here my up carbon, right? Which means this is also an up carbon, and then that's also an up carbon, okay? And I know with up carbons, right, the axial bond is up, is axial, right? And then the equatorial bond is down, okay? Now, you don't have to show all of the hydrogens at each one when you have a substituent. So then once you decide that, you need to add your substituents. So we're gonna draw this again, right? And so here I'm gonna put my hydrogen, and then here I'm going to put my CH3, okay? And that is one of the conformations, okay? Then, so that's our first conformation. Then you need to do a ring flip. Okay, and in this ring flip, we are going to push this up and push that down, okay? And so when we do that, and we show the flipped ring, we now draw our parallel lines this way, and then that one goes there, and that one goes there, and then we go up and up. And now we have ring flipped, okay? So basically what we've done is we've converted the up carbons to down carbons and vice versa. Okay. Then, right, step 3 is to add the substituents. So, right, when we look at this, now I'm actually going to do this up here, all of a sudden, this is now a down carbon because it was an up carbon right here before. So it's an up carbon and we've switched and now it's a down carbon. And so when it's a down carbon, then, right, The axial bond is down, and the equatorial is up. So it's the opposite. Okay. So then when we add the substituents, okay, and we look at that, what we're going to see here is the hydrogen is in the equatorial position, and then the methyl is in the axial position, okay? And this is our second conformation, right? And we've gone from axial to equatorial with our hydrogen, and our methyl group has gone from equatorial to axial. So we see those flipping back and forth, okay? Now, the two chair conformations of cyclohexane that we've been talking about, this conformation here and this conformation here, are different, okay? When you have a larger axial substituent, like CH3, it's much larger than the hydrogen, right? These create a destabilizing and unfavorable, what we call 1,3 diaxial interactions, okay? And so what that means is if you look here with the axial one and you come down here, when this is down, it can interact in that axial position with the other two groups that are also down here. So all those axial hydrogens and that methyl group are really close together, and so we get a big interaction here. When it's in the equatorial position, it's pointing out into space, so there's just a lot more room in the equatorial position, and so it's more stabilized, right? So the larger group for the more stable conformer, you're going to see that in the equatorial position. So when we look at the equilibrium between this conformer and this conformer, it stays 95% stays in this position here, right? Because bigger groups are more stable in the equatorial position. That's what we see. Right? Now, the larger the substituent, on the six-membered ring, the higher the percentage of the equatorial conformation at equilibrium. All right. So if you look here, this is a tert-butyl group, and if it's in the axial position, it's not very stable at all. And so at this doesn't even have an equilibrium. What we see is the only conformer is here in this equatorial position because that's where there's more room, right? So we have looked so far at cyclohexane with no substituents, cyclohexane with one substituent. So I'm sure the burning question in your heart is, Dr. Pierce, can you have two substituents on a cyclohexane ring? And the answer to that is yes. And so those also have some different conformers. And so what we see here are, what we're looking at here are two different 1,2-dimethyl cyclopentanes, okay? One has two CH3 groups on the same side of the ring, and then one has the CH3 groups on opposite sides of the ring, okay? Now, these isomers are called stereoisomers, okay? Now, let's talk about cis and trans, okay? The prefix cis and trans are used to distinguish these two stereoisomers. The cis isomer has two groups on the same side. Okay, so here's the deal. That's either going to be shown as both wedges or both hatches, the hatch lines, all right? So that's what you're looking for. Both of these are wedges. They're on the same side of the ring. I love alliteration. The way I remember this is cis, same side, right? It's all got that s sound. Then we have the trans isomer. And that trans isomer, you have two groups, right, on opposite sides of the ring, okay? And we'll get into double bonds later. So just right now, opposite sides. And what we see here is one of these is a dash and one is a solid wedge. Okay, so we've got the hatched, wedged, and the dash. So you will have some combination of that. So you'll have one wedge and one dash. And that's the pattern you're looking for there. Now, I want us to look at an example of how to draw chair conformations when you have two substituents like we see here. And to do this, we are going to look at 1,4-dimethyl cyclohexane, which also has a cis shown here and trans shown here isomers. Now, these have two possible chair conformations. So let's look at, and what we're going to look at first is trans 1,4 dimethyl cyclohexane and how to draw that. So for trans 1,4 dimethyl cyclohexane, you need to pick two carbons, right, located at the 1 and 4 positions. Right? Then you need to classify them as up or down. Okay? So you're going to pick the two carbons and you're going to classify them as up and down. Now, I've already got this here for you. And so we've got a carbon here, 1, 2, 3, 4. And we look here and we say, okay, look, right? If this is up, that's down. This is up, that is down. Okay. Then you need to draw in the substituents. And so when we look at the up one, we say, okay, I know with the up one, this axial bond is up. And I know with the down one here, this axial bond is down. And so you are going to add the substituents. Now, when you do this, right, the trans isomer must have one group above the ring, which means it's on an up bond, right? And one group below the ring. Which means it's on a down bond. Right? And so this is called a diaxial arrangement, okay? Because, right, we have this in the axial position and this in the axial position. Then, right, and that's our first conformation. Then if we do a ring flip, right, which is what is going on right there, we push this down and we push that up, and now both of these are in the equatorial position, right? So a ring flip converts those axial bonds to equatorial, okay? So both are now in the equatorial position. So when we look at the two conformations that we just walked through how to draw, we see that here's our diaxial conformation, where we've got this CH3 up, this CH3 down, and then we have the diequatorial conformation, where these two groups are equatorial. These are not equally stable. B is much more stable because both the CH3 groups are in the equatorial position. So this means it is lower in energy. Right? Now let's look at the cis isomer. A cis isomer, right, has two groups on the same side of the ring, either both up or both down. So when you draw a cis isomer has two groups on the same side of the ring, right? Either both up or both down, right? So in this example, right, we have conformations C and D here, okay? And what we see here is that the two CH3 groups are drawn in the up positions here. And then when you go through a ring flip, they're also in the up positions here, because we're going from axial to equatorial here. Now, I want you to notice, right, that each of these has one equatorial and one axial CH3 group. And that makes them equally stable. Okay. Now, the last part of this chapter talks about redox reactions. And the reason redox reactions kind of fit in here is because alkanes undergo combustion. That's one of the few reactions they'll undergo, which is a redox reaction. And so I just briefly wanted to review redox reactions really quickly here. If you have oxidation, you're going to increase in the number of carbon electronegative atom bonds. So that would be an example like Z would be oxygen, right? Or nitrogen. And then oxidation also could result in a decrease in the number of carbon-hydrogen bonds. Reduction results in a decrease in the number of carbon-oxygen bonds or an increase in the number of carbon-hydrogen bonds, right? One is one and one is the other. So when we talk about carbon, the most reduced form of carbon is what we see in an alkane here. Then with an alcohol, right, we go through more oxidation till we get up to CO2, which is the most oxidized form of carbon. So instead of looking at redox numbers like you do in general chemistry, here, when we're comparing a reaction, we can look at the number of carbon-hydrogen or carbon electronegative atom bonds and how they change. So this for us ends chapter 4. We are going to go over a lot of this in class. Please try the practice problems. And as always, if you have any questions, please feel free to stop by my office.